Hi everyone, I'm Lily. I am giving you the talk on basal ganglia and disorders of the CNS. This is a topic that I think lots of people struggle with because there's lots of kind of double negatives. I think it's hard to kind of conceptualize what exactly the basal ganglia is. But in saying all of that, you don't actually have to know so much of this in detail. Um, we'll be going through a bit of detail, but I'll make sure I point out the kind of key things they need to know. Um, and also, I don't think the basal ganglia itself is very examinable. I think, if I can remember correctly, there was one question that it was a kind of a repeat question that they use every year on some basal ganglia kind of circuit. But the main thing about basal ganglia is kind of the pathology, and then from the pathology, the drugs, so like the Parkinson's drugs, is the main thing. But still kind of important to know basal ganglia and also appreciate its role in allowing for movement in one of its jobs. So, oh, there we go. Summary slide. This is essentially what you need to know. I would come back and follow up kind of on this after we go through the whole talk. But this is the need to know stuff, and all of this will be covered in today's kind of little lecture shoot. The main starting point I think is important to realize is that I always struggle to kind of understand what exactly the basal ganglia is or did, because I didn't understand its actual role in movement. In my mind, if I want to do a movement like touch my nose, all I have to do is just my brain has to think of a plan. It sends the plan down, my upper motor neuron to my lower motor neuron, down through the spinal cord, then goes onto the muscle, the nerve kind of synapses onto the muscle, and the muscle initiates the movement. However, movement is not just kind of a linear process. It's not just a descending kind of process. There's lots of feedback required. You can imagine, I'm going to touch my nose. I have to be able to, if I overshoot, be able to make sure that I can correct that. So that's kind of proprioception. That's also being feedback, so I can refine it. There's also things that the cortex might be involved in planning the movement, storing movement actions, sending that response. But the actual initiation of movement is done through the basal ganglia, is regulated through the basal ganglia and thalamus, which is what we will discuss today. So let's go into the basal ganglia. First key learning point is that the basal ganglia itself is not a location, so to say. There's no, it's not like a nerve root it's all there together. It's kind of spread all throughout the white matter of the brain. And we can see that here I think this is this is a cross section through the brain. And this shows that the basal ganglia is actually a collection of nuclei. In the speaker notes, you can see the actual exact location of each of these nuclei, but it's very much not important to be able to know where they are. Potentially for neuroanatomy tutes, it might be helpful, but for the exam, I don't think it's very clinically relevant. We'll just quickly go through the main things. So we have our caudate nucleus, which is at the top and the bottom. That's because if you imagine if we cut through a sagittal plane, you'd be able to see the whole thing running in almost a C shape, reverse C. So that's why you can see in the top and the bottom. In this slide, we have our subthalamic nucleus, our substantia nigra. We have our globus pallidus, which is made up of both the internal, external, pituum. I don't really know how to say that. And that's the main things, which are kind of structures, nuclei, collections of nerves, which make up the basal ganglia. Important to realize is that running through the basal ganglia is this thing called the internal capsule. And we'll get to that at the very end, why that's important. The internal capsule itself doesn't have any relevance to the basal ganglia actions. And nice. This is another diagram taken kind of from a different view, showing where the relevant sections of the basal ganglia are. Again, I don't believe it's important to know where the basal ganglia exact components are. I think it's much more important to understand what it does. And just understanding that there's lots of nuclei, there's lots of kind of small little nerves throughout the brain that come together to form circuits which allow movement to occur, and they also refine movement. Just over here is a diagram. I think it was taken from a PSP in the past, which was taken from a student who kind of really does a great job illustrating where each thing is within the basal ganglia in relation to each other. Great. So essentially the broad role of the basal ganglia is this initiation of movement. So it forms a feedback loop with the cortex and the thalamus. We'll go into the feedback loops in a bit. But it forms a loop with the cortex and thalamus to either allow movement to occur or to stop unwanted movements from occurring. It also has other roles in like learning reinforcement and behavior as well, but we're kind of focusing more of it on a movement kind of issue level. These are the main nuclei involved in the basal ganglia. And essentially the basal ganglia is just an integration kind of set of nuclei, which I guess all parts of the CNS is. But it receives information, it kind of processes that, and it sends back out the information to either allow movement to occur or to stop unwanted movement from occurring. It's the main thing. So let's go into the pathways. This is a summary slide for the pathways. I always remember looking at this kind of pathway and being like, oh, this is the most confusing thing in the world. I don't know how I'm ever going to remember this. And to be honest, you don't need to remember it. That's why this is the need to know slide. And this is to really memorize anything beyond this, I think personally would be slightly overkill. But in saying that, I did memorize the whole thing and it didn't serve me at all, but that doesn't mean it wouldn't. I think it's more just important to know that the direct pathway allows for movement to occur, and the indirect pathway stops movement from occurring, stops unwanted movement from occurring. And whether we choose a movement to occur or not is based on the presence or absence of dopamine. And dopamine is released by the substantia nigra pars compacta, which is this part over here. It's this little blue section. And this dictates whether we have the direct pathway or the indirect pathway. And either, so essentially whether or not movement is allowed is dictated by the presence or absence of dopamine. Great, so let's start with the direct pathway. So for the visual learners, we have this diagram here, and I actually think the diagram's a great diagram. So for the cortex to do any movement, it has to bypass the basal ganglia system. And you might ask, why is that? So the thalamus, this VLO is the section within the thalamus, which is involved in the output of movement. But the thalamus always wants to excite the cortex. It's always trying to get the cortex to, you know, initiate movement. You can think of it as kind of the annoying kid always poking the bear, trying to get to initiate movement. So in order to stop the cortex from always initiating movement, always just having random limbs flying everywhere, the thalamus is held under control by the basal ganglia. And here, the part of the direct pathway involved in of the basal ganglia involved, we have the striatum and the GPI SNR. Its role, the basal ganglia here, is to hold the thalamus on a tight leash to stop it from kind of aggravate or pushing the cortex to initiate movement. So the cortex is like, I want to start a movement. I want to touch my nose, for example. So the cortex sends a sign out to the striatum, exciting it. The striatum's normal role is to inhibit the GPI SNR. So this excitation of the striatum allows it to do its job of inhibiting this section here. The GPI and SNR always are holding the thalamus on a lead, so it's always inhibiting it. But because the striatum has been excited and releases its inhibition onto this GPI and SNR, the GPI and SNR can no longer have its leash on. So it's inhibiting the inhibitor is what they say. And that then releases the thalamus from its control and allows the thalamus to excite the cortex. So the cortex can then go and initiate movement. And then if the cortex wants to do an action or something again, it does the same process. So we just do another summary. Cortex excites the striatum. The striatum then can inhibit the GPI and the SNR. The role of the striatum is always to inhibit this. The GPI and the SNR then is no longer, because it's been inhibited by the striatum, the GPI and SNR can no longer inhibit the striatum. Sorry, the striatum has inhibited the GPI and the SNR. And because the GPI and SNR always inhibit the thalamus, its inhibition stops the kind of the hold it has on the thalamus and allows the thalamus to go and excite the cortex there. So that's our direct pathway. So direct for movement, how we initiate movement. This is our indirect pathway, which is the other side of kind of the spectrum, where the cortex comes and excites the striatum. It wants to initiate a movement. The striatum, we're then going on this pathway, and this pathway is chosen because there's no dopamine, but we'll go into that next. The striatum then goes and inhibits the GPI. So the GPE, globus pallidus externus. The globus pallidus externus can no longer, it's meant to inhibit the subthalamic nucleus, but can no longer inhibit the subthalamic nucleus. So now the subthalamic nucleus can go and excite the globus pallidus internus SNR, which is what we had earlier. And because this is excited, it can now inhibit the thalamus. And because the thalamus is inhibited, it can no longer excite the cortex. So action cannot be started in the indirect pathway of stopping the ability for movement or unwanted movement to occur. So just a summary there again. Cortex excites the striatum inhibits the globus pallidus externus, which is our GPE. The GPE can no longer inhibit the subthalamic nucleus, the STN. The subthalamic nucleus is now freed to excite the globus pallidus interna, substantia nigra, and therefore it's no longer inhibiting the thalamus. The thalamus is no longer on a leash. The thalamus is now on a leash. It's been inhibited because this structure has been excited, the globus pallidus and SNR. And the globus pallidus SNR, because it's been excited, does its job to inhibit the thalamus, and the thalamus cannot inhibit the cortex. And that stops that loop from occurring. Now, which loop are we going to choose is always the question. And this is always based on whether we have dopamine or we don't. So dopamine is released from the substantia nigra pars compacta. So this SNC, we have an image going through the whole thing as well. And if we have dopamine release, we select the D1 pathway, and it excites this to allow this to happen. So we choose the direct pathway. And we stop the indirect pathway because we're inhibiting the indirect pathway. If there's no dopamine, we can't inhibit this pathway anymore, and we go through the indirect pathway, stopping movement. So the main thing is that if dopamine is present, direct is chosen, so D for D, and we can facilitate movement. If there's no dopamine, we choose the indirect pathway and we can't initiate movement. This is a summary of them both together, and kind of this over here is the direct, this is the indirect pathway. And here is the kind of these images were actually taken from the lectures of in 2021 that we were given, just screenshots. And I think maybe it was David who gave us a lecture, I can't fully remember. But I think it's good to kind of visualize where things are, and kind of this is all the same thing in the feedback loops. I don't find this one as clean as other ones, but other people might find it beneficial to understand. So those are we've gone through the basal ganglia, has its roles, the nuclei within it, the loops involved, and now we're on to our disorders. So the main two disorders are Parkinson's and Huntington's. Parkinson's is an issue of the direct pathway. You can no longer choose the direct pathway. Huntington's is an issue of the indirect pathway. We can no longer go through the indirect pathway. So let's start with Parkinson's disease. This is an issue where we have there's damage and loss of the substantia nigra, loss of the dopamine neurons in there, which is the reason not fully understood. So we can no longer release dopamine. And because we can't release dopamine, we can't choose that direct pathway. We can't go and, the striatum can no longer inhibit the GPI to then allow the release of the thalamus. So you end up with lots of kind of pathology that shows that you can't initiate movement. So you have the defining features here. I would know all these defining features of Parkinson's, of the resting tremor, the rigidity, the bradykinesia, which is that slow movement and postural instability. You can have also other symptoms, which you will go through, I think, in the ICL. And the pathological kind of hallmark is the Lewy bodies. Treatment will be covered later, but essentially you just give dopamine through levodopa, which is a special type of dopamine which can cross the blood-brain barrier. And Parkinson's disease is kind of the classical hypokinetic disorder. So it's that slow motion kind of disorder. And it's because we have damage to the dopamine nerves, so we can't initiate movement because we can't really use our direct pathway. Alternatively, we have Huntington's disease, which is almost the opposite. And this is actually an autosomal dominant neurodegenerative disorder. It's quite a tragic one. People get it kind of when they're just about 30, kind of the onset. And usually this is after people have had children, so they pass it on to their children without knowing. But Parkinson's disease is usually idiopathic. They're not sure of the cause, but Huntington's disease is autosomal dominant. You kind of have these misfolded proteins which kind of build up over time in the globus pallidus externa. And the issue here is that we can no longer use that indirect pathway. So we can't really stop unwanted movement. And it's the classical hyperkinetic disorder, Huntington's disease, because you'll see there's the term like hemiballismus, where they're doing like almost arm circles like this uncontrollably because they actually can't stop the movement from not occurring. And also has other issues with like dementia behavioral changes just due to other issues, degeneration of the basal ganglia. But essentially here, we've lost the indirect pathway. We can't stop unwanted movements, and therefore we have too much movement, which is the Huntington's disease in parallel to Parkinson's disease. That's kind of all on the basal ganglia. This is just one note that I'll put on internal capsule, which is only relevant because of the anatomical position kind of squeezed within lots of the nuclei structures of the basal ganglia. And I actually think we were given an exam question on this. So the internal capsule, in summary, is almost like a highway which carries all the fibers, the motor fibers of like the corticospinal tracts and also some other kind of motor tracks down from the cortex through the brain into the spinal cord. And it's this white, so the white section is not the internal capsule, it's just here. And the issue there is, it carries all these tracks. And the thing there is that if you have a stroke affecting this internal capsule, just here is caudate, here we have our globus pallidus and patumen, which makes up our what's called basal ganglia, and here's just our internal capsule. We have our anterior limb, which is these tracks. The main thing to know is the corticospinal goes through the posterior limb, and the genital has the corticobulbar tracks. But if you have a stroke within the internal capsule, this is on a little artery called the anterior choroidal, which is a perforating branch from the MCA. middle cerebral artery, you essentially cut that whole highway off. So even though there's nothing wrong with the muscle, there's nothing wrong with the initiation of movement, because you're not allowing anything to travel through, any information to travel through, you get total hemiparesis along the contralateral side. And that is kind of a differentiator from other kind of bigger strokes, or an MCA or a PCA or an ACA stroke. That pathology usually only affects upper limbs, or maybe in the face, or it affects lower limbs more. But a anterior choroidal stroke, even though it's a much smaller artery supplying a much smaller space, it actually has quite devastating effects because of the pathway it's supplying of this internal capsule. Yeah, so those are my slides on the basal ganglia. I hope they were helpful. Again, I think the summary slides will be the most beneficial because they have kind of the key information. But I wouldn't stress too much on really hounding down all the details. I'd want to know more kind of the big picture things of the direct pathway allowing movement, and the indirect pathway allowing us to stop unwanted movement, and then the presence or absence of dopamine allowing either the indirect pathway to go or the direct pathway to be chosen. And yeah, thanks everyone for watching. Hopefully it was helpful.